Hi everyone. Welcome back to Dave's Math Channel. This is my fourth video in a series called Practical Math. And today I'm going to talk about a very famous and very counterintuitive math problem known as the Monty Hall problem. And I'll explain the problem in a minute. First, I want to give you a little bit of background. Who was Monty Hall? Well, Monty Hall was a game show host. He was the host of a very popular game show called Let's Make a Deal. I used to watch this show. It was on in I guess the late '60s and early '70s. The guy standing up, the MC, that's Monty Hall. And the way that the show worked was the contestants would wear these really wild costumes, and he usually picked the contestant was wearing the wildest costumes, so they kind of went all out to look really crazy. So he would pick them, and then it was a little like Deal or No Deal. I mean, he would have all these prizes behind boxes or curtains or doors, and then he'd give the contestants option of picking a door or a curtain. You could keep your prize or go what's behind the curtain, things like that. So there's always risks involved. And another thing that made it interesting was he had these fake prizes. They were known as zonks. And they were things like sometimes they'd be animals, like they'd be goats. And like I mentioned, the Monty Hall problem actually does involve two goats. I'll get to it later, but a goat is really just a zonk. So there were certain prizes that contestants would win. He'd call them zonks, but really they wouldn't win anything. It's just their way say his way of kind of making a joke out of it, saying you lost. But the problem refers to this is the Monty Hall problem, and it was based on the big deal, which was the last feature of every show. So whoever was winning by the end of the show would get to do what was called the big deal, and the way that worked was there was a grand prize was always a car. So if they picked the right door, they would have a chance of picking one of three doors, and there was always a grand prize. I think it was a car, maybe there was more, but just for this problem, let's just simplify it and say that the grand prize was a car that was behind one of the three doors at the end of the show, and the other two prizes we didn't care about. I mean, on the show they really were prizes, but they weren't really great prizes, like maybe a washer and dryer or maybe a sewing machine or something. Everybody wanted the car. So we'll just call the bad prizes zonks or goats. So to simplify the problem, let's say that there were three doors and one of the doors has a nice fancy car behind it. The other two doors have goats behind it. And the way the big deal worked was that Monty Hall would first ask the contestant to pick one of the three doors. And you would think, if he's just picking randomly, that there's a 1 in 3 chance that he'd be right. Right? I mean, that's what it seems like. But that wasn't how it ended. So that after you picked a door, he would open one of the other doors because whether or not you picked the car, whether or not you picked the grand prize, there was always at least one door left that still had a goat behind it. So the next thing Monty Hall would do was he would open one of the remaining two doors and show you a goat. And then he would ask the contestant, he would ask them whether they want to keep the door that they originally picked or switch. And they had that option. And you would think naively, and this is the way most people thought about this problem. They thought it wouldn't matter if they switched or if they stuck with the original door because the thinking is that just because Monty Hall showed you one of the doors you didn't pick, that shouldn't change the odds that you picked the car, right? Because it's not going to move the car around, right? The car can't move behind a closed door, so you would think that wouldn't change the probability. It should still be 1/3. Actually, that turns out that it's not true. And I'll explain that in a minute. It's a very counterintuitive result. It actually turns out that the contestant is better off switching. Here's what happens. So if the contestant sticks with the original door they picked, they have a 1/3 chance of winning. If they switch after Monty Hall shows you the goat, they actually have a 2/3 chance of winning. So the probability is you're better off switching. That's the bottom line. And it's a very counterintuitive result. And it was at first this problem was first analyzed in 1975 by this guy here. He's a biostatistician named Steve Selvin. And I just learned this today. The problem became most famous because of another person, Marilyn Vos Savant. She was running a journal column. She was actually she was when she was doing this was like I think in 1990. She did an analysis of the Monty Hall problem. I don't know if she figured it out independently of Steve Selvin or if she had learned of it from him. But she was considered like I think she was listed in the Guinness Book of World Records as being the having the highest IQ in the world. I think she's still alive, by the way. She might even still be running this gossip column. Um, but she I think she was tested having an IQ of 228, which is astronomical. I mean, that's way higher than Einstein's IQ. I have a hard time believing this. I don't even know what IQ means, to tell you the truth. I think there's so many aspects of human intelligence. It's very misleading to give one number to someone's IQ. But well, for what it's worth, she was very very smart. I'll grant you that, and she understood the Monty Hall problem. She popularized it, and she did an analysis of it. What I think is interesting when I first learned about this, um, I actually um, I didn't really believe the result myself. It's a very counterintuitive result, and I learned a lot more. Like she got a lot of criticism for her analysis. She analyzed the problem correctly and said that the contestants better off switching. They have a 2/3 chance of winning if they switch, only a 1/3 chance of winning if they stick with the original door. She got a lot of people, even professors, like a lot of people, a lot of math experts wrote her back and said, "You don't know what you're talking about." They said what I just said. The car isn't going to switch doors. You don't know basic probability theory, stuff like that. It turns out she was right though. And the thing that the contestant, I mean, let me just, yeah, I'll get to this in a minute. But the thing that, the people who were criticizing her weren't realizing is that Monty Hall, he wasn't just like opening up a random door. He already knew where the car was. So, the fact that he shows them a particular door after the contestants picks their door, that actually gives them extra information. You wouldn't think it does, but he already knew where the car was. So anyway, it turns out that him giving you that extra information actually helps you. And it helps you enough to know that you should switch once he shows you where the goat is. And I'll do a detailed analysis of the problem in a minute. But just to give you an idea why this makes sense, imagine instead of just 3 doors, there were, let's say, 20 doors. So here's 20 doors shown here. I don't know why the space in the top left is a blank, but let's imagine this scenario. Imagine you pick one of these doors at random. You only have a 1 in 20 chance of being right, right? So now imagine Monty Hall already knows where the car is. Say the car was in door 20. That's the blue door shown here. Say you pick door 5. So now what's Monty Hall gonna do? Imagine instead of just showing you one of the doors with a goat, imagine he shows you all 18 doors with a goat, that weren't the goat you picked. There's always going to be at least 18 doors left with a goat, right? So whether or not you picked a car, maybe you were lucky and picked a car. And then, there's still 19 doors left with a goat. He's going to show you one of them. So then, what should you do? Should you switch, or should you? If you just happen to be lucky and pick the car, you shouldn't switch. But that only had a 1 in 20 chance of happening. It's not. You was a 19 out of 20 chance you picked the wrong door. But Monty Hall already knows where the car is. In this case, it's behind door 20. So he's going to show you all the other doors you didn't pick. And then, the fact that he didn't show you door 20 should give you a clue that the car's behind door 20. I mean, how likely is it that you have just happened to pick the right door? He showed you every door except door 20. And what are you supposed to believe? That you just so lucky and picked the right door? Or that Monty Hall knew that it was behind door 20 and showed you all the other doors? Shouldn't you switch? Well, of course you should switch. And if you think of it that way, it makes a lot more sense. So that's kind of what's going on. It's that extra information Monty Hall is giving you that gives you a very good clue of where the goat really is. So, if you want to do a detailed analysis of the problem, you can do this tree diagram here. I don't want to go through all the way through this tree diagram. It's pretty complicated. You have to look at all the conditional probabilities. But if you actually work them all out, you'll find out that the chance of you being winning the car if you don't switch is only 1/3, and if you do switch, it's 2/3. Very counterintuitive, but you know, actually, I'll simplify it. Instead of going through this whole tree diagram, I'll try to explain it in my own words. So remember, there's two events in this problem. The first event is the contestant picks the door before Monty Hall gives them any information. The second event is Monty Hall gives them the extra information, and they have the option of hitting, you know, sticking or switching. So the second event is they either stick or switch. So let's just analyze it. Suppose there's sort of two possibilities for the first event. Either the contestant was lucky and guessed the right door, which has a 1/3 chance of happening. Say the car was behind door one. It really doesn't matter which car door was behind, but say the contestant was lucky and picked the right door, then then they shouldn't switch in that case. When Monty Hall shows them a goat, if they switch, they're going to be wrong. They won't win the car, but that only has a 1/3 chance of happening. Now, suppose there's a 2/3 chance that they picked the wrong door. They picked a goat, but now Monty Hall knows where the car is. He's going to show the contestant the other goat, and now if the contestant switches, he'll get the car. And there was a 2/3 chance that he was wrong initially, and if he switches in that case, he will win the car. That has a 2/3 chance of happening now. You know, if he didn't switch, he'd only have a 1/3 chance of winning the car because he's sticking with his original guess, which only had a 1/3 chance of being right to begin with. So that's the right way to think about the Monty Hall problem. Like I said, a very counterintuitive result, but I think it's a really interesting math problem. A really interesting problem in statistics, and it just shows you how counterintuitive math can be sometimes, especially statistics. I don't know. Statistics is kind of a weird area of math. It's the easiest branch of math, I think, to lie with. Um, there's even a book called Liars, Damn Liars, and Statisticians. And, you know, you can really pull the wool over people's eyes with statistics and probability. So, anyway, that's my video. Thank you for watching. Long live math, and I'll see you guys next time.